This video is going to cover the second day of section 5.2, linear approximations and differentials. Just a little recap from yesterday, we talked about calculating the linear approximation, and what this means is that you are using the equation of the tangent line at a fixed point called C, an x value C, to find y values of different x values along that tangent line. And so our tangent line isn't any different from what we've done previously, except we're going to start using L of x, giving the tangent line, a name of a function. So L of x equals, and then your y value at that fixed point plus the slope at that fixed point times x minus c. The linear function can be written in different ways, and it depends on what information that you have and that you are given. So we're used to the tangent line looking like this, where your L of x equals your y value plus the slope times the change in x's. Another way you could look at it is that x minus c is your horizontal displacement from the fixed point. So if you're not given the two different x values, you're not given x equals 1 and c equals 0.5, but you're given that the delta x or the dx is 0.5, you would plug in 0.5 for dx instead of 1 minus 0.5 if we weren't given those two values. So that's one more way to write it, is just by changing that. But then the last thing is, if you have f prime of c times dx, let's say you're not given the slope of the tangent line, but you know the approximate change in y, you could find the equation of the tangent line as the y value plus the approximate change in y value, and use that to calculate any approximations. So just another little recap. Remember, dx and delta x are always going to be the same. It's your horizontal displacement from your fixed point. So you find it as f of x minus f of c. Just a reminder that c is your fixed x value. That's the x value that you have your tangent line. dy is your slope of the tangent line, so f prime of c times dx. And dy is usually not equal to your delta y. So remember, dy is the approximate change in y using the tangent line. Delta y is the actual change in y, and you can find it a couple different ways. So here's f of c plus your delta x. So if you know your change in x, you can add that to your c and then subtract f of c. So same thing as f of x minus f of c if you have those two different points. So just a little warm-up. This is what we did yesterday. I'd like you to work on this individually. You are given the equation f of x equals x cubed. What I want you to do is write the equation for the linear function L of x that best fits at x equals 2. Use that linear function to approximate f of 1.9 and f of 2.01, and then calculate the errors in those approximations, and then find the values of dx, dy, delta x, and delta y at x equals 1.9 and x equals 2.01. So go ahead and pause the video and come back for the answers. So the first part, write the equation of the linear function. So we said at x equals 2, when you cube 2, you get 8. That's the y value. Then the derivative would be 3x squared, and when you plug 2 in, you get 12. It said to use the linear function to approximate f of 1.9 and f of 2.01. When you plug those into the tangent line, you get 6.8 and 8.12. The third step was to calculate the error in the approximation. So remember, this is the absolute value of f of x minus f of c. So you're going to get two different errors because we were using two different x values. F of 1.9 minus L of 1.9, you should have gotten an error of 0.059. And then the error between 2.01, that's right, sorry. F of 2.01 minus L of 2.01 equals 0.000601. And then lastly, I made a table for this one. It said, what are the values of dx, delta x, dy, and delta y at x equals 1.9 and 2.01? Remember, dx and delta x are the same. It's just your f of x minus f of c. So 1.9 minus 2, negative 0.1, and 2.01 minus 2 to get 0.01. dy, remember, is your slope times your dx. So 12 times negative 0.1, you get negative 1.2. And for 2.01, you get 12 times 0.01 or 0.12. And then your delta y is the actual change in y. So this is your f of 1.9 minus f of 2 to get a negative 1.141. That just means that we have moved to a lower y value from our fixed point. And then f of 2.01 minus f of 2 is 0.120601. So just to show you a couple of graphs of this. So the red graph is your x cubed and the blue is your equation of your tangent line. So as you can see, the cubic doesn't look anything linear. The blue line is close, but if we were to zoom in on that, and I'm going to zoom in on the point 1.9, so here is 2, here's our fixed point, and then here's our x value of 1.9. The red line and the purple dot is the actual y value at 1.9. The blue line and the orange dot is the y value on the tangent line. And so that shows it's pretty good. There is a little bit of space between the two, so that's why we had an error of 0.059. If we were to zoom in the other way by 2.01, so here our fixed point 2 is down here on the bottom left, 2.01 is in the top right corner, you can see that because we're only 1/100th of a way from 2 instead of 1/10, our error was much, much smaller. And so you can barely see the difference between the function and the tangent line, and you can just barely see a difference between the actual y value and the approximate y value. The part that's new for section 5.2 is writing equations of differentials. So we are going to write an equation for dy, and it's very, very simple. It's something that we've been doing the entire time. The only thing is now we're going to get away from dy dx and we're going to write it as a dy equation. And so in order to do that, you just find your dy dx equation and then you multiply both sides by dx. So the example that I have here is e to the 3x times cosine of x, and we are going to write the equation for dy. So what we're going to do is find the derivative of this. We need to use product rule, 2d1 plus 1d2, and then at the very end we are going to multiply both sides by dx. So dy, here's my 2d1 plus 1d2, and then what I'm going to do is kind of simplify it, make it look a little bit better, and multiply both sides by dx. And so then this is what I get. I just rearranged it to be 3e to the 3x times cosine of x, and then this negative sign makes it minus e to the 3x sine of x. That whole derivative should be in parentheses, and then when you multiply both sides by dx, the dx goes at the very end. And so this is called the differential dy. We're just going to practice doing this for this section because coming up, we're going to be getting into antiderivatives and integrals, and you need the dx to be on the right side. The next example I have is the natural log of tangent of 5x, and it says write the equation for dy. So this one's just the chain rule. There are 3 functions here. So dy dx equals 5 times secant squared of 5x divided by tangent of 5x. So the derivative of the inside, next layer is tangent, and then the 1 over your tangent of 5x. The last thing to do would be to multiply both sides by dx. And so you can either leave it like this, or you could also put your fraction in parentheses. So very simple, nothing new. The only thing that is different is bringing the dx to the other side. And just make sure if you are using product rule that you have your derivative part in parentheses. So what you're going to do for the remainder of class is finish the back of the worksheet that you got from yesterday. You can check your answers with the answer key and hand it into the box. Have a great day.